Rob, if you want to start now.
Okay, welcome. Have you got me there, Hashim?
Yes.
Okay, welcome everybody. Just like to briefly talk about the issues that we have in the mining and quarrying conveyor industry in relation to bearing reliability. This will be followed up next week by another webinar which will talk about the technologies that we use to try and increase the reliability. But essentially, this one is all about the different issues which occur in operation. I guess the first place to start would be looking at some surveys. This is a result of recent surveys of various mining companies. And as you can see from this slide, there's been 31 times the system, the conveyor system has been selected as being the top 3 when it comes to reliability issues, much more so than gearboxes, motors and others. So it is a #1 problem for the mining and quarrying industry. And 3 main issues with conveyors: poor reliability causing lost production. And as most of you know, lost production costs can be extremely high. There's high maintenance costs, in other words, higher costs per tonne in producing the product. And also another thing which is a major concern is the high number of accidents, so safety related issues. There's a study done in an iron ore mine in Sweden over a 2-year period, and the predictive maintenance records typically came up with bearing damage as being one of the primary issues in relating to conveyor reliability. So it certainly is a problem in the industry. Another audit that was done some time ago in Australia at an iron ore mine, there were 11 conveyors were inspected with a total of 39 pulleys and 78 bearing housings. Typically, if you look at the chart below and look at the occurrence of the identified problems, contaminated lubrication grease point, 100%. Every single bearing housing had a contaminated lubrication grease point. Very highly contaminated surroundings. Sometimes the lubrication point was very hard to access. Sometimes there's very little or no evidence of lubricant or grease exit points, etc. So lots and lots of issues relating to contamination and improper lubrication as being the main issues regarding conveyors. The costs, as I said before, it can be substantial. A coal industry conveyor carrying between 1,000 and 3,500 tonnes per hour can cost as much as $36,000 to $100,000 per hour in lost downtime. Iron ore mines, the costs can be anywhere up to $1 million per hour, so very costly. Looking at availability, this is a calculation showing how to calculate availability of machines, and best in class is considered to be more than 92%. Most conveyors in the mining industry do not have best in class availability. And something to note there that just a 1% increase in availability can significantly increase production. So anything that we can do to increase bearing reliability will ultimately give you conveyor availability. Safety, a study was done in the USA, and that came out saying that 43% of injuries were caused while a worker was performing maintenance or checking a conveyor. 24% of fatal mining accidents involve conveyors. So safety is very high on the very high when it comes to reliability of conveyors. So the more we can make a conveyor reliable, the less maintenance that needs to be carried out. So therefore it becomes safer in general. Let's have a look at the typical bearing failures that we see. The first one there is subsurface initiated fatigue. Now, subsurface initiated fatigue is the normal way that a bearing should fail. Now, it's related to the number of revolutions and the load on the bearing. So over a long period of time, a bearing can fail, but it should be a long period of time. From my experience, I don't think I've ever seen a bearing from a conveyor that has failed due to subsurface initiated fatigue. In other words, the bearings that we see that fail in the mining industry in conveyors typically are failing due to premature failures, not old age failures as they would be designed into. So typically the loads on conveyors are in general relatively low. The speeds are relatively low. So therefore the bearing life should be extremely long. It should be in excess of 5, 10, 15, 20 odd years. But typically it's not. But like I said, the failures are very rarely, if ever, caused by subsurface initiated fatigue. So what failures do we see? We see failures due to surface initiated fatigue. Now, surface initiated fatigue is caused due to generally a breakdown of the lubricating film, inadequate lubrication, insufficient lubrication, etc., etc. So lubrication or ineffective lubrication leads to surface initiated fatigue, which would be one of the major problems that we see with failed bearings in conveyors. Certainly abrasive wear is a very high cause of failure too. That's where you get a lot of contaminated particles get in, mix up with the grease and cause a lot of wear that takes place on the raceways, the rolling elements, in the cage pockets, etc. Adhesive wear can occur. Adhesive wear is the mechanism where rolling elements are not adequately loaded. It's quite often found with conveyor pulleys that the rolling elements come into the loaded zone. The bearing is perhaps a high clearance bearing. The rolling elements have slowed down when they slow down in their rotation when they leave the loaded zone. There's perhaps a large amount of grease in the bearing, which helps to retard the rotation of the rolling element. And then when they come into the loaded zone again, they get rapidly accelerated, slide across the raceway and cause damaging adhesive wear. Moisture corrosion, certainly that's a problem. Certainly we see situations where a conveyor is stationary for some time, water gets into the bearing, it gets in through the grease, the rolling elements are sitting stationary and we get rust appearing on the raceways and the rolling elements. This can come from the normal environment, it could come from hosing down, for example. So moisture is a major concern. Threading corrosion. Threading corrosion is an issue where you get micro movements of mating components. So for example, if the inner ring of the bearing is pushed up onto the adapter sleeve and it's not tightened up sufficiently, there can be micro movements occur between the inner ring of the bearing and the sleeve and the shaft. These micro movements cause the surface asperities to break off, and then they will very quickly oxidize in the presence of air and become what's called fretting corrosion. It's also quite often seen on the outer ring of the bearing in the housing, especially if the housing is out of shape or of poorly supported. False Brinelling, yeah, it's something that we see, and typically it's more than likely caused during transport. So, for example, a pulley could be rebuilt in a workshop and then transported several hundred or thousand kilometres by truck, and with the continual vibration, we could end up with false Brinelling damage on the raceways as a result of the vibration, the cyclic vibrations caused during transport. Okay, so typical bearing damage. Again, we see indentations from debris. Now, most conveyor manufacturers build and design a very good product. The selection of the bearings, the housings, etc., are usually suited to the environment, suited to the application. Most rebuilders do a very good job in repair jobs. However, many issues occur on site where there's maintenance issues which then cause damage, then cause issues with bearing reliability due to poor maintenance procedures or perhaps operational procedures, which these can't necessarily always be considered from the design point of view. The maintenance issues may not necessarily be related directly to the bearing itself. It could be, for example, the wear skirts aren't adjusted properly, and then that allows product to build up, spill all over the bearing housings, and then we get ingress of contamination. We could get blockages in chutes due to operational issues, where the product could be too wet, for example, and it ends up blocking up, and then you get product pouring all over the bearing housing. So issues like that, not necessarily related directly to the maintenance of the bearing housings and the bearings. So we identified that conveyors typically operate in a harsh environment, wet, dirty, extreme temperatures. We can have conveyors in the mining industry, North Queensland, Western Australia, subject to tropical conditions, cyclones, etc. We get a lot of exposure to high pressure washdowns, contamination even occurring during assembly in the workshops, etc. So because of all this, we have to look at increased greasing to purge contamination out of the bearing housing. We need certainly extra maintenance, better seals perhaps, extra sealing compared to what was originally designed in there, taconite seals, sealed bearings, for example. Typically, we see lower than expected service life because of these contamination conditions, and certainly increased costs. A lot of conveyors are difficult to maintain because they're elevated. They're up high, they're in hazardous locations. It makes it difficult to make repairs in the field. It quite often requires the use of large cranes, etc., to be able to pick the pulleys up and to make it easier to repair. So the repairs aren't necessarily well made. They're probably done in a hurry. They're not done in a proper way. You've got production screaming that we've got to get the conveyor running. So the jobs isn't necessarily done properly. So all of these sorts of things need to be taken into consideration. If we look here, and hopefully this will work, I've got just a very small video of an actual situation here. Let me just give this a couple of minutes to start up. Okay, so what we've got here, hopefully everybody can see this on their screen. We've got a typical conveyor here. What I was getting at before regarding the things that are done on site which can cause problems. If you notice here, this whole side, for whatever reason, is being cut out with an oxy torch. This is allowing all the product to spill off the belt and pour all over the housing and the seals. Now, why that was done, I've got no idea. Why it wasn't rectified, I can't answer that question either. But as you can see, it doesn't help the bearing situation when you've got wet product like this coming up the belt. And then we end up with it pouring all over the bearing housing. Now, what type of sealing arrangement is going to work best there to try and stop that product from getting in? Another one here, this is on the same conveyor. So you can see the build-up of product, see water dripping down from above. It's a very wet environment, but why is the water dripping down? Okay, it's pouring down from here. Instead of going down this pipe, it's spilling out over the top and dropping down onto the bearing below. So again, we've got a maintenance issue here, which is potentially causing issues. Another one here on the same conveyor again. This is where the water's coming from, off of this pulley down into here, but then unfortunately it's going from there down onto the bearing below. So there's many issues out there which are caused as a result of poor maintenance that takes place. Some more examples. Here we're seeing, just change this pointer. In here somewhere, there is a pulley. The belt's here. Pulley's in here somewhere with all this spillage that's taken place. Again. Here we've got the situation where we've got a seal, a labyrinth seal, not fitted correctly, but no evidence of grease continually being purged out. How do you get in here and manually grease something like this? Perhaps it's not being done properly. So issues such as spillage that's not being cleaned up creates other issues. If we have the opportunity to look inside a bearing housing, this is one here, and we can pick out issues, things that are causing us problems. To start off with, we've got a grease nipple here on the taconite seal. It's rusted. There's no signs of grease there. It's not attached to an automatic lubricator. So the suggestion here is this seal has not been receiving grease to purge contamination out. Inside, we see old dried grease mixed with product. We're seeing dried grease in this groove around the outside of the bearing. Now, this groove should be in line with the grease nipple hole in the center of the housing cap. And this is the main grease supply into the bearing. So if this is dried old grease, there's no evidence of recent grease. The bearing obviously hasn't been re-lubricated very well. Over here, we've got large amounts of freestanding water in here. We've got corrosion on the outer ring of the bearing. So this tells us straight away that we've got a major issue with contamination. Another one. Again, we've got no grease in this central groove. When was this bearing last greased? We've got wear that's taken place on the sealing lip of this oil seal. So the contamination's been coming in through the labyrinth seal and wearing the sealing lip away on this seal. And again, we're seeing grease with freestanding water droplets. Corrosion. So again, it's getting moisture corrosion into the housing as well. So on the subject of lubrication contamination, certainly we're getting it in through the past the seals. The other thing is we might be getting it in directly from the re-greasing procedure. Here, for example, we've got our grease guns in the maintenance store. Look at the end of this grease gun. How much of that contamination is actually going into the bearing, especially if it's being put into a grease nipple, which is like this, where it's not cleaned off first. So here we've got a manifold with grease nipples, which is to be feeding this bearing. So which line goes to which? How much grease goes into each grease point? This is a seal. This is a seal on the housing. Over here, we've got grease lines going to a seal on the gearbox. And this one's feeding the side of the bearing. The bearing does not need too much grease, but the seals certainly do. So does the greaser know how much grease to put into each of these grease nipples? What about this one? We've got a grease nipple missing completely. And over here, we've got one on the seal, which you can't get to. So again, we've got major issues regarding contamination getting in and poor lubrication. Another one's here showing 1, 2, 3, 4, 5 grease points on one housing. Not necessary. Why have these? What are they doing? What's this one doing? What's this one doing? Nothing. You're better off going directly into the bearing and to the seal. Another one here where you've got automatic lubricators. We've got automatic lubricator set up here. You've got a grease line here, which is over 3 meters long. It disappears up here somewhere to another automatic lubricator. These small gas-filled lubricators in general will not pump grease these sorts of distances. The recommended maximum length for those hoses is only 0.5 meter to 1 meter long. And then we get incorrect lube setups where you've got confusing and contaminated lubrication points. Where do these go to? How much grease is supposed to go in which? And again, we've got the situation here. You've got a grease nipple here in the center of the housing to lubricate the bearing. Is that one getting lubricant? Maybe it is, maybe it isn't. We've got these going to the seals, but how much grease gets put in which one? And I think this is finally on lubrication. We've got, again, small lubricators feeding large bearings on lines that are too long, restricting grease flow. Look at the size of this bearing, thinking about how much grease should go into the seals. How can a very small lubricator of this size put sufficient grease into those seals to purge out excessive contamination? This is the type of thing where you require larger lubricators or a full online system to be able to put the appropriate amounts of grease into these applications. Small amount into the bearings, large amount into the seals perhaps. Okay, let's have a look at housing assembly issues. Now, this could be taking place on site. It could be done by contractors. It could be done off-site repairers. Some issues that we've come across in the past. This is showing the split line. The housing base would be underneath here with the cap on top. They've put sealant on the split line. Too much sealant on the split line. It's been, looks like a silicon sealant, and it's extruded it into the lubrication groove. That means that when you add lubricant into the center of the bearing, it's not going to go fully around this groove and get into the lubrication holes, which could be down at the 6 o'clock position, for example. The other thing is it's dry. There's been no lubricant put in there. So the first few applications of grease into that bearing when it's being operated will only be filling up the hose and then maybe filling up the groove, and then later on perhaps getting into the bearing. The other issue is there's not enough grease in the whole bearing assembly itself. There's only a small amount. Well, the bearing's packed, but there's hardly anything in the housing, and there's hardly anything in the seals. So more grease is required during assembly. Here we've got one which the cap's been removed and inspected, and it's been in storage. It's been in storage for some time. Look at the colour of the grease. We've got rust all over the lock nut and the shaft. There's been very little, if any, grease packed into the housing or into the grooves of the labyrinth seals. There's very little grease in the groove on the housing. Around the outer ring of the bearing. There's no sealant on this face. Now, the previous slide showed excessive sealant and the wrong type of sealant. This is showing no sealant. So we have to get that bit right. We've got to put the right sealant on there and the right amount of sealant. All right, alignment issues. Two alignment issues to consider here. One is the alignment of the pulley, and the other is the alignment of the housing. Both of those have to be considered when the pulley is installed into the application. Okay, so with belt tracking, the belt tracking is not done properly. The belt is going to move towards the end of the pulley. A couple of things can happen there. Firstly, we could have issues like here, for example, it's showing that the belt has actually been rubbing here on the housing. It's been tracking off the edge of the pulley right over here to the housing. First question is, how is this grease nipple going to be lubricated if the belt's running over here? Won't be the case. Take these ones, for example. How much axial load does that add to the bearing loads? Because the belt now is running off the edge of the pulley and it's forcing the pulley in an axial direction, which could potentially overload the bearing, which is taking, or the locating bearing, which is taking the axial loading. Let's have a look at alignment. The maximum recommended misalignment of the housing and bearing relative to the pulley is about 0.25, 0.3 degrees. If you exceed that value, either by having the housing on an angle relative to the pulley on an angle relative to the housing, then we can have issues whereby the seals could open up. So a typical housing seal can only accept between 0.3 and 0.6 degrees total misalignment. But on the left-hand side, we see that the labyrinth gap has opened up, which will allow more contamination to get in. On the right-hand side, we can see that the seals are actually in contact. So that means now that this rotating ring is in contact with the stationary outer. So we're getting friction, heat, potentially a lot of wear. So we have to ensure that we keep our misalignment angles within acceptable limits. Another one here showing misalignment. If we look at the opposite sides here, you can see that there's a gap. The sealing lip is no longer in contact with the shaft. But on the other sides, the seals are completely flattened out. So again, we have an issue where we're going to get massive damage to the seal on one side and contamination getting in the other side. Otherwise, this is the same housing. This is also showing the housing tilted over on an angle. So at the top, there's a 0.2 mil gap to allow water and contamination to get in. But at the bottom, it's completely compressed flat, which is putting a lot of force on this sealing lip. Severely misaligned bearing can lead to short bearing life. So when you look at this bearing, this is before the cap gets bolted on. The rollers are actually sticking out past the outer ring of the bearing, putting huge stresses in this area, which will lead to very short bearing life. Support surface flatness and condition. Sometimes because of the very wet environment, we can get a lot of corrosion take place on these support faces, very poor support faces. In some cases, we get people putting shims underneath the housings. Now, shims underneath the housings means that the housing is no longer supported underneath the base. The support surface should be flat. The bearing housing will distort to suit the shape of the flatness of the base. If the base has got a high spot on it, then the housing could well distort to suit that high spot when it's bolted down, which means that the housing bore could go out of shape and the outer ring will also go out of shape. Here's another situation where we've got a conveyor pulley here, and the belt's wrapping around the pulley and heading back in that direction. There's shims at either end of the housing. The load direction from the belt tension is in that direction. As you can see here, there is no support under here, which means that we've got potentially high belt tension loads deforming the housing in that direction to the left. This can cause the housing to deflect inwards at the split line, making the housing bore oval. The housing bore is oval, then the outer ring of the bearing will also go oval, creating high loads in those areas and subsequent reduced bearing life. Another thing we commonly see is poor fitting skills. A bearing of this size will never be able to be tightened sufficiently using a hammer and cold chisel. You'll end up having it coming loose on the shaft. The other thing is the same guy is using feeler gauges to check the clearance in the bearing. I would suggest that whilst he's wearing good protection on his hands for the purpose of fitting the bearing, you do not have the feel required to measure accurately the internal clearances in the bearing. So incorrect methods are used. The result of incorrect or insufficient tightening is typically the sleeve and the bearing coming loose after a period of time in service. We get the resulting threading corrosion. As soon as you see this type of appearance on the bore of the bearing, sleeve, there's a couple of things to think. Firstly is the sleeve or the shaft to conforming correctly to dimensional geometric form, or has the bearing not been tightened sufficiently? In most cases, you'll find that the bearing has not been tightened correctly onto the shaft. Another picture there showing an adapter sleeve, which has obviously been subject to not being tightened enough because of the threading corrosion all over the outer surface of the sleeve. So Bearing is not tightened correctly, it will come loose on the shaft. It can allow the shaft and the drum, the pulley, to move axially. We look at this photo here. The end of the shaft has moved relative to the labyrinth seal. And here we see a worn down section of the shaft where the bearing has come loose, the sleeves come loose on the shaft. Another photo here showing where the bearing's been loose on the shaft. Now, the purpose of an adapter sleeve is to mount the bearing such that it's a correct tight fit on the shaft. An adapter sleeve needs to go onto a shaft which is as perfect in shape, condition, size as a bearing that's being fitted on a shaft with an interference fit. It has to be in good condition. This shaft is not in good enough condition to mount a bearing on an adapter sleeve. Housing bores must be checked. They've got to be measured to ensure that they are correct dimensionally and also conform to the right shape. The bearings are made with extreme precision. So if the shaft is out of roundness, what's going to change shape? The shaft, or perhaps the sleeve, the inner ring of the bearing. What about the housing bore? If it's out of shape or out of size, what's going to change shape when you assemble it? The outer ring of the bearing or the housing? Improper fits can have a detrimental effect on bearing life. So if the bearing's too tight, then we're going to lose clearance in the bearing and it's going to run hot. If it's too loose, the outer ring, for example, could do a lot of creeping in the housing, or the sleeve will come loose on the shaft. So it's strongly recommended that we take several measurements. We take measurements in 3 places along the shaft and 4 places around the shaft, and we record all these on a chart like this. We do the same in the housing bore. We take 3 or 4 measurements along the bore and in several places around the bore. We record them all. Then we compare the smallest to the largest. And the smallest to the largest shouldn't deviate by a certain amount. That certain amount's referred to as a form tolerance. So for different sizes, there will be a certain form tolerance to suit. The other thing to consider is, even though you can do some measuring and get some good values, the surface of the shaft may not still give you enough surface contact. So by using a small straight edge and some Prussian blue or bearing blue, we can run the straight edge backwards and forwards across the journal in several places around the shaft, and we can get a picture of how much surface contact there's likely to be between the sleeve and the shaft. The photo on the left is showing only small contact. We've got a very large low point here in the middle, whereas the one on the right is showing very good contact all around the shaft. Shaft and housing cleanup. Look, in the repair stage, we do get fretting corrosion. What do we do about the fretting corrosion? Certainly don't get into it with flap discs or emery tape. Try and remove any fretting corrosion with Scotch-Brite pads, maybe some steel wool, wire wool. You don't want to create any more further damage. Perhaps because the shaft that has a fairly large tolerance when it has sleeves on it, there might be sufficient material left. If the finished size is up on the high side of tolerance, it might be able to be lightly skimmed and repair that surface. Couple of other things to consider. Sometimes the pulley design, especially in, say, older designs or maybe cheaper designs, does not allow for improved sealing. This is due to the fact that the bearing and housing are mounted very close to the shaft. There could be, as shown here, an increase in shaft size, and actually there's a key here holding the pulley to the shaft. So there's no axial space in here to be able to put improved sealing in. Likewise here, you've got a shaft which has been manufactured. This would originally have had a housing perhaps with felt seals, and the shaft protrudes through the felt seal. Things like this means that you've got a seal in this area, which is an additional point where contamination can get in. This would be better if the shaft was made shorter and finished inside the housing and an end cover put on. Housing form can cause issues. We're talking about housing form is the bore of the housing. Some non-SKF housings do not comply with the correctly, dimensionally, and with form accuracy. There are some housings out there which are very poor quality. They have low quality cap bolts. The housing bores can be out of round. The housing bores can be too large. So again, remember, the outer ring of the bearing will conform to the shape of the housing bore. So if the housing is not of good quality, potentially it could be out of shape, which will then distort the outer ring of the bearing, causing bearing life, which is not as intended. And finally, the same thing with sleeves. There are some non-SKF sleeves that don't comply with dimensional and form accuracy. This is showing a sleeve which was fitted, bearing was fitted correctly onto a shaft. The shaft was conforming entirely. It was nice and round. There was no taper, no out of shape. The bearing was a good quality bearing, but the sleeve was of a cheaper manufacturer supply, and the result was that the bearing and sleeve and shaft were not fitting correctly together. There's too much micro movement causing the subsequent fretting, corrosion and damage. So that brings it to the end of this webinar. Like I said, it was just really to highlight a lot of issues that we see out there in the mining and quarrying industry regarding pulley bearing reliability. Next week's follow-up webinar will introduce various technology offerings that SKF can provide, and a lot of these technologies allow improved reliability based on a lot of these issues that we do see out there. So that's the end of this. If you've got any questions, please enter them via the chat function. And I thank you for your time. And Thursday, I believe, same time next week, will be the part 2 of this webinar. Thank you.